Hello student. So in this video we are going to show that this function which is written in your screen fx is equal to 0 when x is rational number and fx is equal to x when x is irrational number. We want to show that this is continuous at x is equal to 0. Before doing that, I want to prove some claim. The claim one is mod of fx is less than equal to mod x. So this is a claim. I'm going to prove this, and after proving this, I will use it to show function function is continuous at x is equal to 0. So before going into proving this claim one, let us recall the definition of mod x. So this is the definition of mod x. Mod x is equal to x if x is greater than equal to 0, and this is equal to minus x if x is less than 0. So the property of this is the property of mod x that this function mod x, that if you take x belongs to any number, then this mod x always returns a value that is greater than is equal to 0. Why? Because suppose suppose let's take a real number. X belongs to R. Either x is greater than equal to 0. Let's say this is our case 1. Then according mod x will be x only, and x is greater than equal to 0. So mod x is greater than equal to 0. Now case 2, x is less than 0. Then mod x is equal to, use this definition, since x is less than 0, mod x is minus x. Now in this equation x is less than 0, multiply by minus each side. When you multiply by minus, the inequality reverses, so minus x is greater than 0. So this minus x is greater than 0. You combine this inequality, you will get mod x is greater than 0. So since mod x is greater than 0, you can actually write mod x is greater than or equal to 0. When we write greater than equal to, when do we write greater than or equal to? If either it is greater than 0 or it is equal to 0. So in this case it is greater than 0, so we can write mod x is greater than or equal to 0. So now similarly the meaning of less than equal to sign is less than or equal to. So I want to prove the claim 1. Okay, before prove, in this case, before doing the proof, here also we need to take cases, because the definition of fx, it is dependent on whether x is rational or x is irrational. So let's take the case 1. X is, let's say, rational. So what I want to prove? I want to prove this one. The mod of fx is less than equal to mod x in this case. And I will also, there will be different case. Case 2, x is irrational. In this case also, I will show that mod of fx is less than equal to mod x. So first this case, what is fx? If x is rational, look at this definition. If x is rational, then fx is equal to 0. So 0, this is equal to 0. Now use property 1. Property 1 says mod x is greater than equal to 0. So we will use this property 1. Mod x is greater than equal to 0. So this is by property 1. Now case 2. In case 2, fx is equal to what? See here, if x is irrational number, fx is equal to x. So mod of fx is equal to mod x, and this is obviously, so mod of fx is equal to mod of x. Now so what is the meaning of less than equal to? Either it is less or equal to. In this case this is equal to, so obviously fx is mod of fx is less than equal to. So now in both the cases I have shown that mod of fx is less than equal to mod of x. In this case also mod of fx is less than equal to mod of x. So for any r, any real number, it is either rational or it is irrational. In both the cases I have shown that this thing holds. So claim 1 is proved. This claim 1 is proved. Okay, now what we actually wanted to show is that we wanted to prove that, yeah, yes, we want to prove at x is equal to 0 the function is continuous. Okay, so let's first uh, recall the definition of continuity at a point A. Okay, I'm gonna write it quickly. F is said to be continuous at x is equal to A if for every epsilon greater than 0 there exists delta greater than 0 such that fx minus fa is less than epsilon for all x, I mean let's write whenever x minus a is less than delta. So we have to find, I'm going to highlight this point, we have to find a delta. we have to find a delta such that this condition is true whenever this condition is true. I mean, if you have to find a delta such that if x minus a is less than delta, then fx minus fa is less than epsilon. Okay, so in our case, a is equal to 0 because we are checking continuity at 0. So let's put a is equal to 0. So we want to prove that if x is less than delta, then f fx minus f0 is less than epsilon. Okay, so now this is what we want to prove. Okay, so we have to exhibit there exists a delta. I mean, we want to prove that f is continuous at x is equal to 0. So we need to exhibit there exists such a, I mean, there exists a delta such that this condition holds true. Okay, so let's first what is f of 0? 0 is actually rational number. At rational number the function take I mean 0 value, so let's put that here. So fx minus 0, so it will be mod of fx only. This condition we need to check. I am saying that we need to find a delta, right? So I am saying that choose delta I am saying choose delta is equal to epsilon. Then if this is true, if mod of x is less than delta, then I want to show this thing, right? So I will now use the fact claim 1. Recall claim 1. Claim 1 is mod of fx is less than mod of x. So we will just use that mod, then mod of fx this is less than this one using claim 1. We have already proven this, so we can use this. Now since x is less than delta, this thing, and our delta is equal to epsilon, so this is equal to epsilon. So mod of fx is less than epsilon. If you combine all of this is what we get. So if mod of x is less than delta, then mod of fx is less than epsilon. That is what we wanted to prove. So we have proven that f is continuous at x is equal to 0. We had to find a delta, right? There exists delta. This is the delta, and of course you can also check this is greater than 0 because epsilon is greater than 0 and we have taken delta to be equal to epsilon. So epsilon is greater than 0, So delta is equal to epsilon, so delta is also greater than 0. And when we are done with the proof. So now you realize why claim 1 was, I mean, why I was trying to prove claim 1. Because claim 1, if you can so use the claim 1, if we can prove the claim 1, then we can actually use it here and we can complete the argument here. So that's it for now.